Welcome to my YouTube channel. Today we're going to have a look at the heat flow equation, first in one dimension, later on in more dimensions, and later on we are going to employ some GPU ways to compute the solutions to the heat flow equation. But yeah, let's just dive into the theory of the heat flow equation. The heat flow equation is a parabolic partial differential equation that is governed by this equation here. So you can see that the change or the rate of change of our function is linked to the curvature of our function multiplied by a numerical constant, that's the heat conductivity. And yeah, in one dimension this curvature operator, which is also known as a Laplacian, is just the second derivative in x, but for more dimensions that generalizes to the Laplacian operator, which is given here. Okay, now that we know what we are going to solve today, we need a method of solving these kinds of equations. And the method that we're using today is the Crank-Nicholson scheme. The Crank-Nicholson scheme is a scheme that is used to solve these kinds of equations, and the nice thing about this scheme is that it is unconditionally stable, meaning it does not depend on the discretization in time or the discretization in space for it to converge, which makes it super easy to use it to solve these kinds of equations. But if we use the Crank-Nicholson scheme, we don't have an explicit formula, but we get an implicit formula, but we will dive into that a little later. Okay, so let's formulate how we would derive that scheme. So if we have a look at our PDE up here, you can see that on the left-hand side there is a time derivative of our function, and yeah, we want to know the value of the function at the next time step from our current time step. So what we do, we don't treat this function in this form, but we integrate it on both sides. Then we get the function in our spatial, or at our spatial point I, at our point in time n+1. So this right here is just the integral over the derivative, that's just the function at the next point in time minus the function at the current point in time. And on the right hand side we have to integrate over time from our current time to the next time step. And now we approximate this integral by a simple trapezoidal rule, meaning we take we average the curvature of the function at our current step, at the current time step, and at the next one. And for these second derivatives, we simply employ a central difference scheme for the second derivative, which can be proven to be this formula, but yeah, I'm not going to go into that. So now we have the function at un+1, but as you can see, it still depends on the right-hand side, also on points in un+1. So we have to rearrange it to have on the left-hand side only the next steps in time, the next points in time, and on the right-hand side only the current points in time. If we do so, we get this kind of formula where we use an abbreviation for these constants that, yeah, are not too important for this scheme, since we are using an unconditionally stable scheme where we can use or choose R arbitrarily. There are other schemes where you can't choose it arbitrarily, and then it's important what you use here, but yeah, for us it's not too important. Okay, so we have this kind of equation, and as you can see, you can always formulate this as a matrix equation where yeah, A and B are in this case tridiagonal matrices, but in higher dimensions they are going to be banded matrices, but yeah, they're still going to have many entries on the diagonals or close to the diagonals and not so many on the far away from the diagonal. Okay, since we said that we're unconditionally stable, we can just choose our constants so that r equals 1, then this term here just vanishes and we get our final scheme that we're going to use to solve the heat equation. Okay, for the heat equation we for sure need an initial condition and boundary conditions, where we're going to use as boundary conditions just the Dirichlet boundary condition, where we know the value at the end of, or at both endpoints of the interval. Okay, so yeah, let's jump into the code. So first we're going to use some libraries. So for sure we're going to use NumPy. We're also going to use SciPy since there are some sparse libraries, but more on that later. Some libraries for plotting and making animations. Yeah, then of course we're going to have to solve a system of linear equations. So yeah, we're going to use some solvers for these. There are some traditional solvers like the Gaussian way to solve these equations, and iterative ways which are not convergent to the exact solution but are way faster. Yeah. Okay, now we have our imports and we're going to think about our initial condition and our boundary condition. So first of all, we need to write down the domain where we want to solve the heat flow equation, and in doing so we have to think about how many points we have to use to discretize our domain. From first principle, this scheme is unconditionally stable, but we can't make the distance between 2 points too large or we'll encounter numerical issues. But so yeah, we'll just take 1000 points, and by this equation up here you can compute how much that would be if we had a interval from 0 to 1, or yeah, whatever you like to choose for your length of your interval. So what we're going to do is we're going to set all values to 0 and going to make it really hot in the middle of the interval, like that we're going to make it from 40% to 60% of our interval, and then we're going to make it hot, and elsewhere it's going to be 0. Then we have to use boundary conditions for sure. So I'm just going to use the simple boundary conditions to make it 0 at the boundary, but we could also easily just use arbitrary values. So. But yeah, for now we're going to use 0. And we have to apply these to our computational grid, that's not going to change anything, but if they weren't zero, that would change something. Okay, so now we'll have a look at how that's going to look. Yeah, as you can see, in the middle it's quite hot, and at the else it's 0, and at the both endpoints it's also 0. Okay, now that we know our initial configuration, we're going to have a look at this system of equations. If you have a look at here, you see that the ith point only depends on the I minus first and the I plus first point, meaning we're going to have a tridiagonal matrix with 4s on the diagonals, because yeah, the ith point gets multiplied by 4, and negative 1s on the or first off diagonals. Okay, the way we're going to do that is we're going to create here a simple array with n minus 2 values, since our computational grid is going to be including the both boundary conditions, but these are not going to change, so we have to exclude them from our solver. So yeah, we get an n minus 1 times n minus 1 matrix, and yeah, the diagonal entries are just going to be some factor times this array once. Okay, we can have a look at it. Yeah, as expected, it's just ones, and it's going to be 989 entries. Okay, now we're going to create a tridiagonal matrix that is done using the diags method from the SciPy Sparse library. What we're doing is, we just give the values that we want to write on the diagonal. In our case, it's just going to be some multiplicative of 1s. So we're going to, for the first off diagonal below the diagonal, we're going to need 1s. But if you think about the matrix, it's going to have one less entry than the diagonals. So we're going to take all values except the last one. Then for the main diagonal, we're just going to use the 1s. And for the first off diagonal above the diagonal, it's just again going to be negative 1 times the 1s with the last one missing. So now we specified what values we want to write into the matrix. Now we have to specify where we want to write them. And how that's done here is we need to give the distance to the main diagonal, meaning on the diagonal, the distance to the main diagonal is 0. On the first off diagonal below, it's negative 1, and on the first above, it's just 1. And yeah, as I said, we're going to use sparse matrix, since the most values in this array is going to be zeros anyway, and that's going to really slow us down in solving this this system of equations. But it's also going to use very much storage space, which I don't have, and which for large systems, especially in 2-dimensional or 3-dimensional systems, even large computers don't have. So we're going to use a sparse matrix, but we're going to have a look at it, if it looks like we wanted it to. And yeah, as you can see, we have exactly this negative 1 for a negative 1 scheme and zeros elsewhere. Okay, for the solver, the solver is going to be especially effective if we transform it to a certain format, but yeah, that's not too important. Okay, let's think a little more about the last point that I made, that it's way more memory efficient. We can, for a normal array, we can just have a look at the size by a.n bytes. Yeah, of course we need to create an array from there. So that's in bytes, but I find megabytes way more intuitive. So yeah, if we just were to use the matrix A as a normal array, we would use 7 megabytes. And if we were to use it as a sparse matrix, then of course, or the way that the sparse matrix is stored, that is that we store the values that are non-zero, and we store the positions at which these are stored, and like that we don't have to think about all the entries that are zero, because we only store those that aren't anyways. But to compute the size, we need to sum all these up. So that's the data. That's just an array where we can again bytes. Then we have to also consider the indices at which these are stored, and these are given by these two values. Okay, again we want to convert it to megabytes. And here you can see it's way smaller. And you might think 8 megabytes is not too bad, but if you think that the size is going to scale quadratically if we're going to 2D and cubically if we're going to 3D, that's going to get really big really fast. So yeah, that's why we use sparse matrices, even though if for the one-dimensional case we could solve it without using sparse matrices. Okay, now if we go back to our linear systems of equations that we have to solve, we found the left-hand matrix that we're going to need to iterate, but we still haven't found the right-hand matrix, where if you have a look at it, that's just going to be a tridiagonal matrix, but the main diagonal is going to be 0 because on the right-hand side it doesn't depend on ui, but only on the values next to it. So it's going to be a tridiagonal matrix with 1s above and below the diagonal, but 0 on the diagonal. So yeah, we're going to create it from just like we did above. Okay, yeah, as you can see, on the main diagonal it's just zeros, and on the first two off diagonals it's going to be 1s. Okay, now that we have the both matrices that we're going to use to solve this equation, we can actually try to solve it. Okay, what we're going to do here is we are going to define how many steps we want to do. In our case, we're going to use 5,000 or maybe 50,000. Then we want to think about which values we actually want to compute, since in our array we have 1,000 points including the boundary condition, but the boundary or the points at the boundary are not going to change because they're fixed by the boundary condition. So we just want to think about the interior points, and these are going to be from 1 to, or from the first to the second to last. Yeah. And because we want to make an animation out of that, we're going to have to store the state of our grid in each iteration. So we're going to make a large array, and it's going to have t-end entries in the first dimension, and then in the second dimension we're going to store the interior points, and that's going to be n-2 long. And for the first value in our storage, we're going to just save the current state of the interior points. Okay, then we can iterate. Okay, what are we going to do? First, we can compute the right-hand side. So we just use this matrix vector product. So we use SB times the interior points. And yeah, if we do that, we don't consider the boundary condition. So for boundary condition where the values at the boundary are not 0, we have to apply the boundary condition after we compute this matrix vector product. So we have to save them first. So the point which is closest to the left boundary is going to be the 0th point of the interior points, but if you have a look up here, the 0th point is going to be affected by the point left to it and to the point right to it. The point left to it is going to be the boundary condition that we already know, but the point right to it we don't yet know, or we don't know, and we have to save it because afterwards it's going to change. So that's going to be the second point in our interior points, but yeah, it's going to be 2 away from the boundary Similarly on the right side, it's going to be the second to last. Okay, then when we have computed this this right-hand side of our equation, we have to apply the boundary condition. So these are going to be the first and the last point. Okay, now that we have our right side in the right format, we can solve this this linear system for these un+1. That's just going to be a simple Gaussian algorithm. If we use this SP solve, that's just the Gaussian algorithm for sparse matrices. And the solution of this method is going to be, for our next iteration, the next interior point. So we always update these points. And if we want to animate it, we have to store these. So yeah, now we have our loop, and I'm going to run it, and it's going to take a while, so see you in a bit. Okay, now it took 17 seconds. That's not too bad. Yeah, now we can have a look at what we computed. I have here a little script that just creates an animation. I don't really want to go into that script, but yeah, I'll upload it to GitHub later anyways. Okay, now the animation just finished. It took way longer than the actual computation, but yeah, let's have a look at the results. Yeah, as you can see, at the beginning it's this rectangular shape, and it smooths out over time, and if we wait long enough, it's going to be 0 everywhere. But yeah, let's have a look if we computed our left and right boundary condition correctly. If we were to set the left and the right boundary to values that are not 0, then we would expect that for large times, here we have to use my -1, that for large times the function is going to be constant on this on the value of the boundary condition. And if we rerun this, we'll hopefully see just that. Okay, so the computation just finished, and yeah, let's have a look if it looks right. Yeah, as you can see, it smooths out again, but now the whole function converges to 10 everywhere. That's just exactly what we expected. Yeah, that's it for today. Next time we're going to have a look at the 2D Crank Nicholson scheme for the two-dimensional heat flow equation, and there we're going to have to think about how to speed up the actual computation and not just the animation, and we're going to do that by using the GPU to speed up this linear system of equations. And yeah, hope you enjoyed it, and see you next time.